This is 2018 Further Discrete. It's the AS paper 2 and it's AQA. Okay, so we've got this table here and we just want to see which of these operations it could be. First of all, we've got 3 and 2. Either we can multiply them to get 6, but we've got a result of 1, so that could be mod 5 because that would give us a remainder of 1. Or we could add them together to get 5 and then we'd have a remainder 1, so that could be mod 4 for addition. So addition mod 4, multiplication mod 5, it must be this one. These two are symmetrical, so it doesn't change the answer whether this one is, given or not. So it must be this answer. We've got this binary operation here. Now, we get this, right, mod 8. We're also told that this equals 6. So if we just replace a with 2 and b with x, okay, and you just plug it into the here, we can expand a little bit to get 30 plus 6x, right? But this is mod 8, which means that we can subtract 24 from this 30 because 8 goes into 30 3 times. Right, so 8 goes into 30 3 times to get 24, but that won't be included because it's mod 8. We're only given the remainder, and so the remainder would be 6 because we're going 8, 16, 24, and then we need another remainder 6 to get to 30. So that's actually the same thing as saying 6 plus 6x mod 8. It doesn't change this because 8 goes into 6x 0 times and we just have a remainder 6x anyways. Okay, we've got 6 plus 6x equals this, but we know that this equals 6, so this actually equals 6, and then you get x equals 0, so this must be your answer. We've got a zero-sum game here with Alex and Sam, and we want to find the value of the game. Right, so if we just look for maximins and minimaxes, what's the worst case scenario for Alex from here? Well, the worst case scenario is that he just gets a 2, right, because that's the least amount. With A2, the worst case scenario would be a 0. And then the worst case scenario with strategy A3 would be a -2. Right, and the best of those worst case scenarios would be 2. Right, so that is the best scenario of those 3. Sorry, did not mean to show that. Okay, and now for Sam, let's have a look. What's the worst case scenario for Sam? Remember, 5 points for Alex is -5 points for Sam. So we're actually looking for the largest numbers in these columns. So the worst case scenario for Sam, for S3, would be 5. And then for S2, it would be 3. And then for S1, it would be 2. Now, the best of those worst case scenarios would be 2, because he loses the least. And for Alex, that would also be a 2, because he loses the least. Right, so, and 2 equals 2, so we've got maximin equals minimax, therefore there's a stable solution, and the value of the game is 2. The play safe strategy would just be that Sam always plays S1, and then Alex always plays A1, right? Because then, if they're just playing their play safe strategy, they're not trying to win as much as possible. The main idea is that they're trying to lose as little as possible. Okay, we've got this network flow, and we want to find the value of this cut here. Now, just be careful. What this actually means is we're just splitting up the source side and the sink side, and we only want to count what goes from the source, right, to the sink, right? So the source is always usually on the left, right? It just depends on how they've drawn it, and then the sink would be on the right. Okay, so if we draw this cut, right, and we've only got A, B, C, D, F, J on the left, so on the source side, and only E, G, H on the sink side. Okay, and we'll just draw a cut that makes this exclusion. Okay, and we just want to count what goes from the source to the sink. Well, we've got a 4 from source to sink. We've got a 9 from source to sink. This, we've got a 4 from sink to source, but we don't include that because we only go from source to sink. So we've only got 9 plus 4 so far. Source to sink 2, source to sink 22, right? So it's 4, 9, 2, 22. You add them up to get 37. And then it says, what does this actually mean? Well, it just means that the maximum flow of the network is either 37 units or less, centimeters cubed per second, apparently. So it's always that much or less. There could be a lower cut. Remember, the minimum cut gives you the maximum flow. So there could be a lower cut, but they've not asked us to check. So either this is the minimum cut or there is one less than it. Okay, list the nodes which are the sources of the network. Well, if something is a source, it only has whatever quantity inside of it. For example, water in here, I'm guessing. it would only be pointing away from it, right? Because you're only pushing into it, you're only pushing out from that one node. So for example, D here, you've only got arrows coming out of it, so that must be a source. Similarly, J, only arrows coming out of it. So for example, if we looked at G, arrows out of it, except for this one going into it, so it can't be a source. So the only sources we've got are actually D and J. Okay, add a super source. A super source is like the main source, which feeds into the other sources, right? So if we just call it S, okay, well, it's only going to feed into D, and it's only going to feed into J, because those are the only sources. And now it must have, at minimum, 28 going into this one to be able to provide a flow of 28 through D to A and then F. Similarly, down here, we'd need at least 194, so that would be 14 here. So that's 28 there, and that's 14 there. I've just added up these and put them there. List the nodes which are sinks of the network. Well, if something is a sink, it will only have arrows pointing into it. It will only ever take in whatever the quantity going through the pipes are, or whatever is going through the network. And so if we have a look, E looks like it could be one, and H looks like it could be one also. Everything else has both arrows pointing in and away from it, other than the sources which only have arrows pointing away. So the only sinks would be E and H. Okay, add a supersync to the T to the network. All right, so supersync T, well, it funnels all of the sinks into one sink, the supersync. So from E to wherever the supersync is, and then from H into that, right, and that's T. Here we've got 22, 24, 30 going into it, right? So it must be able to take in at minimum 30. And then similarly here, it must be able to take in at minimum 15, so 11 plus 4. Okay, we've got this activity network here. Use figure 2 shown below to complete figure 1 above. So we want to complete this first. Okay, we're just looking for the immediate predecessors. So for example, if we look at E, well, what comes immediately before E? Where is E? So that's just D. Okay, and then we're looking at F. Immediately before it is just C and E, right? You could also think maybe it could be B, A, and D, but that's not immediate. Immediately before it is just C and D. Okay, this has no predecessors apparently, and where is it? A H, where is H? H is here. Immediately before it is G, and then I, it would just be F and H. Okay, so that part there is done. Now I've zoomed into this picture here a little bit. Now we just want to complete this activity network. So if we look at all the beginning activities, the earliest that they can start is 0, 0, 0, right? Because you're not going to start negative hours in time, or whenever this is, in minutes or whatever it says. I think it's in minutes actually, right? Okay, if the duration here is 1, right, and you can start at hour 0, the earliest start time of this is just when this one can finish. So it's the earliest finish time of this, which is 0 plus 1, so that would be 1. Similarly here, this one can start when this one's done, and then this one is finished at earliest after the 10th minute. Alright, so 0 plus 10, so 10. And then similarly here, 0 plus 4 would give us 4 for the same reason. Okay, now the earliest start time of this one is just whenever the earliest finish time of that one is. So that's 1 plus 18, so 19. Similar here, 10 plus 12 is 22. And then 4 plus 12 would be 16. However, let's be careful, right? If this one finishes at earliest 16, right, and this one here finishes at earliest 23, then this one can only ever start if both of these are done, because it needs both of them to be done. Now, at the 16th minute, yep, this one will be done, but this one's still going. This one still needs to go up to the 23rd minute. So, in fact, this one can only ever start if this one's finished first, right? Not first, sorry. If this one's finished, because by the time this one's finished, this one's not done, so this one can't start. But by the time this one's finished, they're both finished. That means I can start. So I can only ever start whenever F and H finishes, and the earliest time they both finish would be the earliest time F finishes. So 22 plus 1, which would be 23. Okay, this is duration 2, so 23 plus 2 is 25, and that finishes the activity network. Now we need to go backwards to find the latest finish times. Now, if the latest finish time of this one is 25 and it has duration 2, that means it must have started at the 23rd minute. So this one must finish at latest at the 23rd minute. to be able to finish this one at the 25th minute. Now let's look here. So 23 takeaway 1, that would actually, no, I think I've started down here first. So we've got 25 takeaway 2, same thing here, 23. Okay, now here we've got 23 takeaway 1, right? So that would be 22 here. It's because the latest time this one can finish is at 22 minutes, and so if it finishes at the 22nd minute, it can still, there's still time for this one to finish by its latest finish time. Okay, now up here, 23 takeaway 1, also 22, because if it finishes at the 22nd minute, this one can still get done in time. 22 takeaway 1 would be 21, and then 21 takeaway 18 would be 3, also for the same reasons as I've explained here. 22 takeaway 12 would be 10, 23 takeaway 12 would be 11. Okay, state the activity time, state the activity which must be started first so that the meal is served in the shortest possible time. Now, here we're just looking at critical activities. Now, look at it. Let's look at G actually. It's easier to see it with G. Now, G, the earliest time it can finish is 0 at the 0th minute. So it can start straight away and it can go on for 4 minutes. And then this one can start by the 4th minute. Now, this one has a lot of like wiggle room. You can kind of think about it. This one can finish. This one can start at the 7th minute actually. The latest time it can start, not the earliest, the latest time it can start is the 7th minute, and it would still be done by at least the 11th minute. And it's not like you've held it back that much, right? You wouldn't have held it back at all actually, because these all have wiggle room, right? You can see this one can actually start at the 11th minute. This one can start at the 11th minute, not just the 4th, right? So that's 11 takeaway 4, so that's 6 minutes of wiggle room, right? This one is 7 minutes of wiggle room. That's tons of wiggle room. This one here, it doesn't have any. It has to start exactly at 0 and finish at 10. Like, there's no wiggle room. 10 takeaway 10 is 0. That's no wiggle room. 3 takeaway 1, that's 2. That's 2. This one can start 2 minutes into it. Right, so there's wiggle room everywhere else except for D. There might not be, there isn't wiggle room here or here, because these are also critical activities, but the first critical activity is D, right? So the one that should be started first, that must be D, because it's a critical activity. Determine the earliest possible time at which the preparation of the meal can be completed. Now, if the earliest time this the last activity to start is 23, and it takes 2 minutes, well, that means it finishes at the 25th minute, which we already knew here, which means that this entire thing should take 25 minutes, right? So it would take 25 minutes, but be careful, it says the earliest possible time. Now, at the beginning of the question, they gave us this piece of information. They said it would start at 6:30. So 25 minutes after 6:30 would be 6:55 p.m. Okay, let's see what we've got. It takes 15 seconds to switch on the oven. Okay, the oven must be allowed to heat up for 10 minutes before the spring rolls are put in the oven. It takes 15 seconds to put the spring rolls in the oven. The spring rolls must cook in the hot oven for 8 minutes. It takes 30 seconds to transfer the spring rolls to a serving dish. Complete figure 3 above. So when we're switching on and heating the oven, well, switching on the oven just takes 15 seconds, so that's fine. We also need to heat it. It takes 10 minutes, so that's 10 minutes plus 15 seconds. So in minutes, that's 10:25, right? 10.25 minutes. Putting the spring rolls in the oven and letting them cook. Now they must cook in the hot oven for 8 minutes, and it takes 15 seconds to put in, so that must be 8.25. Right, if you're wondering where the 2.5 comes from, well, a full minute is 60, and then 15 seconds would be a quarter, right? Because it's 15 over 60, which is the same as 1 over 4, which is the same as 0.25, so 8 plus 0.25. Transfer spring rolls to a serving dish. It takes 30 seconds. That's half a minute, so 0.5 minutes. Immediate predecessors. Well, first, to be able to put the spring rolls in the oven and cook them in the first place, we need to switch on and heat the oven. So that's a J. Now, transferring them, the immediate processor, well, we have to have them finished before we can actually, put them on a serving dish. So that must be K, capital K. Determine the latest time at which the oven can be switched on in order for the spring rolls to be served at the same time as the rest of the meal. Remember, the rest of the meal is done at 6:55, Okay, and then here, how long do we have? We have 18 minutes, 18.5. That's 19 minutes for everything all together. Okay, so six. If we do 55 minutes, take away 19 minutes, that's 36 minutes. So this one must start at latest by 6:36. Because if we start this at 6:36, then 19 minutes later it'll be 6:55, and so we'll finish exactly on the same time, and that's fine. That's what we want. Okay, so this is a minimum spanning tree question. We've got this table here. Now, this table isn't very helpful on its own. Personally, I think. I think it's just a bit goofy. So what I did actually is I just drew it out again. I drew this out on my tablet, so it doesn't look amazing, but I'm sure you can understand it. So, for example, from C to G, where is C to G? C to G is 680. Here 680, and then C to K, where is CK? 610. Stuff like that. I've just basically filled it in because I prefer to see it like this. Now we want to find the minimum cost of connecting all the sites to the rainwater collection site. Okay, so you're gonna perform either prims or cruscals to visit every node, but it doesn't actually matter which one you do. Even if you don't know the difference, that's not what they're assessing. They're just assessing that you can actually do it. I can't remember. I think I've gone with cruscals because I think I've just picked the shortest one first. I think. Am I? No, no, no. I'm doing prims here. Prims, they're basically the same thing. Don't even worry about it. Okay, so I've said G to H first of all. That'll be 150, and then the next shortest one would be 310. G to D. So that's 150 plus 310, and then the next shortest one with connected H and D. Well, that would be 680 all the way to K, all the way to C. Sorry. And the next shortest of all of these ones would be 370. So that gets us to R. And then the next shortest one, we've already gone to H, we've already gone here, so we don't need to. We just need to get to K somehow. That must be just 520. And that will have completed our visit to every single node. That's 2030 meters in total. Each meter is 60 pence, so 2030 times by 60 pence gets us £1,218. Linear programming now. Okay, we're just sketching these equations on here, I think. Complete. Yep. Okay. Yeah. So just sketch on whatever's there. I've redrawn it here and then I've enlarged it a little bit. I'll just go ahead and explain my reasoning. So x is between 1 and 6. So let's put x equals 1 and then x equals 6 here. Okay. And then we've got y between 1 and 6. So y equals 1, y equals 6, and then we've got y is greater than or equal to x. I'm just going to assume it's y. I'm just going to think about it as y equals x. So that would be that. Okay, and then y is always greater than x, so it's everything above this line. I'll get to the actual inequalities part of it after. Here we've got y equals minus x plus 11. So minus x plus 11, where is 11 is here, and that gets us this line here. What I would suggest you do is just plug in x equals 0, okay, and then to get whatever the y-intercept is. Well, you kind of already knew it would be what, 11 here. And then here plug in y equals 0 and solve to find what x would be, and then you just know it must be the straight line connecting those 2 points, so that must be this line here. Okay, and we want to have y be less than or equal to 11, so we want to be below this line. Okay, if we're looking at the feasible region now, the place where all of these intersect, right, which would give us the greatest value for the objective function 5x plus 4y, is just, it's called I think it's called the vertex method. I can't fully remember, but the greatest point which satisfies all these conditions must be this one here, because we must be in between these two lines here. Okay, that's fine. We must be in between these two lines here. Okay, we're also fine. We must be greater than or equal to y equals x, right? So that's this entire line and everything above it, and we must also be this line here or completely below. Now the only place that satisfies all those conditions must just be this point here. Okay, that looks to be 5.5, 5.5. So x equals 5.5, y equals 5.5. We've also got this point here. Okay, so that's 5, 6, and then those are all the actual vertices, I think. Yeah, that should be fine. Okay, so we've got 5.5 and then 5, 6. It's easier to actually shade it in. I think they do actually want you to shade it in, but it was quite hard to do on PowerPoint, so it's quite difficult to do this, but it's fine. If you can see that, then it's fine. Plug in 5.5, 5.5 into this, plug in 5.6 into this, see what gives you the greatest value. If you plug in 5.5, 5.5, you get 49.5. If you plug in this, you get 49. This is the great one, so we want that one, and that's our answer. Yep. Okay, we've got a simple connected graph G. It has 7 vertices, and they're of degree 1, 2, 3, v, w, x, and y. Explain why x is less than or equal to 1 and y is less than or equal to 1. Sorry, greater than or equal to 1, greater than or equal to 1 here. If it's a connected graph, then every vertex must connect to, each node or vertex must connect to at least one other node, right? So this must be greater than or equal to 1, this must be greater than or equal to 1, this must be greater than or equal to 1, this must be greater than or equal to 1. You must at least connect to one other person, one other node, sorry. Okay, explain why x is less than or equal to 6 and y is less than or equal to 6. Okay, it's a simple graph, so we're not going to have any overlaps, we're not going to have any loops, anything like that. So you can connect at most to every node in the graph, but you can't connect to yourself. If there's 7 vertices, right, you can connect at most to 6 other people, 6 other nodes. You can't connect to yourself. You can't connect to the 7th one because you're the 7th one. So you can connect at most to the 6th ones, right? Explain why x plus y is less than or equal to 11. So if you look at this, we have one vertex with degree 1, right? So only x or y can connect to it. So the remaining order for the vertex is just less than or equal to 5. That's what I've written here. I hope that makes sense. So like, say, imagine you drew this out and you had, well, you can't really draw it out, but say you had a node, right, and it only connects to literally just one other thing, right? And either it's going to be either x or y. It can't be both because then it would have degree 2. Okay, so if it can only ever connect to one other thing and that thing is x, well, that must mean that the other 5, the other like orders must just be 6 minus 1, so that would be 5. Right, because you can only ever connect to at least 6 anyways, maximum. But then you're kind of like, if at most you can connect to a 6, right, but somebody is forced to only connect to 1, that leaves you with just at most 5 to connect to. It's less than or equal to 5 because v and w could take up like some random like proportion together. Okay, hopefully that makes sense. And then state an additional constraint that applies to the values of x and y in this context. This one I actually didn't get because I didn't think about the most obvious answer, and that is just that they both must be integers. Obviously, that didn't come to mind. I thought it was something more quantitative, given all these other options, but apparently not. So the answer is just that they both must be integers. The graph G also has 8 edges. The inequality used in part AI applied to the graph G. So I think I had to rewrite them all here. Oops, yeah, I did not mean to do that. We're given that v plus w equals 4. Okay, so x plus y is less than or equal to 11. This is going to be the most important one for us here. If if v plus w equals 4, that means we can just sum up all these to find what the total degree is, right? So that gets us 3 plus 2 plus 1 is 6. 6 plus these two, which is 4, which gets us 10. So this here is 10, and then 10 plus x plus y, and that's whatever the total edges is. Now, there's this thing called the handshake lemma. Yeah, I put it down here. The handshake lemma, you will have been taught this. You should know this. If you don't, then maybe keep a note of it because it is in the textbook. But if you have a node and you're connecting to another node, you will always have an even order. Because imagine if I have a node, right, and then I connect it to another one. Okay, the total order is 2, right? Because when I connect it to another node, I'm always increasing the order, right? So if I have one node by itself and I connect it to another one, you have order 1, order 1. Okay, and let's say I connect that second node to another one, so we have order 1, order 2, order 1. So that's 4. Okay, and if I connect the last node to the first node, that will be order 2, order 2, order 2, so that's 6, right? Hopefully that makes sense. I'm not sure if it does. It makes sense to me. If it doesn't, maybe you want to research this in your own time, but it just means that because for each edge that I'm making, I'm increasing the number of nodes by 1, and if I'm always starting off with an odd number of an odd degree kind of, and I'm adding it on, then actually, yeah, then I'm always going to have an even total order. Okay, so whatever the total number of edges is times by 2 will give us the total order. You can prove this for yourself actually if you want. So the number of edges is 8. 8 times 2 is 16. So we know that this here must equal 16. Okay, so we get 16 equals 10 plus x plus y. So we get x plus y equals 6. Now, find all the feasible values of x and y. Well, we know that they have to be integers, so it's actually not too many values it could be. If x was 1, this would be 5. If x was 2, this would be 4. If x was 3, this would be 3. And that gives us those fair solutions. But also be careful. You could have y is 1, x is 5, y is 2, x is 4. You can't really swap these ones, but because they give you the same thing. But you can swap the x and y's for these two here. So you'd actually have 2, 4... plus this one, so that would be 5 solutions in total. Okay. It's also given that the graph G is semi-Eulerian. If something is semi-Eulerian, it means it has exactly 2 odd degree nodes. Okay, so exactly 2 odd degree nodes, and the simple. Okay, yeah, that's just a graph there. I've written on here the values, of x and y. Now, x and y can only ever be 2 and 4, because if it has exactly 2 odd degree nodes, well, here we've got 2 odd degree nodes, right? Which means that everything else must be an even degree node, otherwise it can't be semi-Eulerian, which means that x and y both have to be even, and v and w also both have to be even degree. So we know that x and y just must be 2 and 4, or 4 and 2, right? So I'll just put a box around that, so you know that's that. And then v and w, well, v plus w equals 4, as we've been given from here. Okay, and we know that just must be 2 and 2, because they both need to be even for the graph to be semi-Eulerian, because we already have 2 odd degree nodes. Okay, so yeah, we're just going to draw that down. There's different ways you can draw this. I think this is just the way that I did. I just copy and pasted this down from the mark scheme just because it was easier than drawing it out myself. But yeah, so for example, this one here could be my y with degree 4, and then this one here could be the x with degree 2, and then this could be the v, and then this could be the w, this could be the 1, this could be the 3 here, and that would be it. That's it, finished. That's the entire paper. Thank you for watching.